Hello, welcome everyone to Beyond Tags, Content Discovery with Tripadvisor's Hybrid Graph Search. And I'm handing over to you, Constant, to take it over. Cheers.
Thank you. Hello, everyone, and welcome. We're thrilled to be here at Notes 25 today to talk about the Tripadvisor's Hybrid Graph Search. This project is a result of a collaborative effort by a highly skilled multidisciplinary team. I'd like to take a moment to introduce the core contributors who made this achievement possible. We have Varuni Gang, Senior Principal Machine Learning Engineer, Amir Rad, Senior Software Engineer, and Dan Pan, Senior Machine Learning Engineer. And finally, my name is Konstantin Bazin, and I serve as a development manager. I also invite you to read the blog post, the recent blog post, which is linked on this slide. It provides more details about this project. So let me start with a few general words about Tripadvisor. Tripadvisor is a travel guidance and booking company, and we strive to connect travelers with what matters most for them. This simple goal drives every innovation, every improvement we're doing within the company. On this presentation, we'll be talking about tags. So let's start with what a tag is. A tag is a label which is connected to a piece of content, like point of interest. And in Tripadvisor, points of interest are hotels, restaurants, attractions, any bookable products you see on the site. Tags play a very important role in the navigation of the site. They're used for search and discovery, helping travelers to find what matters for them. They're used for personalization and recommendations, helping us to construct the results which are relevant and matching the user's interests. And they also help us organize the content and navigate through the huge catalog of content we have. As traveler expectations evolve and new trends emerge, tagging data is changing. It's changing all the time, and the big challenge here is to make sure it's up to date. How do we keep the tags relevant? How to make sure the point of interest is not missing a tag it should have? In order to better understand and manage tags, we introduce a knowledge graph, and here on the right side, you can see a subset of the ontology of our knowledge graph. It has the nodes and edges which are relevant for this presentation. So you can see there is a geo node. This is the representing a geographical area. Each geo can have multiple locations. Location is another name for a point of interest. And at the end, the locations or points of interest can have multiple tags associated with them. And there are challenges with managing this data set. There is a process which is deciding which tag should be connected to which locations, and this process is taking a lot of time. As a result, these delays result in incomplete recall, and sometimes we're not able to retrieve all the relevant locations because some of them are just missing tags. In order to improve the situation and provide a better recommendation, we decided to combine knowledge graph with semantic search. For this, we needed a graph database, which is capable of supporting vector indices, of course, for the semantic search. The graph database should be able to perform multi-hop graph traversals, and also it should allow to run graph algorithms and analytics at scale. So we took a look at our knowledge graph and enriched it with a few extra elements. First of all, we added reviews. Reviews are connected to POIs. These are provided by users, and they contain a lot of useful text. They're up to date. We have a steady flow of reviews, and they provide a great description of the POI. Together with reviews, we also added a few different vector indices for geo names, for tag names and descriptions, and for the review text. So let's take a look on the right side, where we'll see how we can match, how we can retrieve the relevant information for the user query restaurants with live music in London. So looking at this query, we can extract a few elements there. The restaurant is a type of content. Live music is a tag, and London is a geo. So with these three elements, with these three IDs, we are able to effectively retrieve the relevant results, relevant POIs. But what if a tag is missing? Here, the vector search comes into play, and we can do a vector search with the live music and retrieve the relevant POIs which might be missing a tag. This also works when the tag just doesn't exist for a new concept, which we didn't create tag for yet. So we decided to use Neo4j, and there were a few reasons for that. First of all, Neo4j provides has a proven track record supporting production-grade systems. It has a built-in vector indices, which allows us to have everything in one place. There is no need to implement cross-system joins. Both the graph structure and the vector indices are in Neo4j. But before we can start using this data, we need to make sure that the Neo4j has the data. So we need to ingest the data there. And this is not trivial because the amount of data you can see is pretty big. We have tens of thousands of geos, tens of thousands of tags, hundreds of millions of locations, over a billion of reviews and contributions. The good news is that Neo4j had no problem handling this amount of data. We still had a couple challenges. First of all, the process which is ingesting the data is taking some time. It wasn't super fast, and we had to do some optimizations. We used process data in chunks, and we also introduced checkpointing. So there is no need to redo the whole process if we need to resume it. The other issue we identified are the deadlocks. When the ingestion is running in parallel, multiple parallel processes are trying to create edges. It is possible to have a deadlock because when an edge is written to Neo4j, both ends, the source and the target, need to be locked. They can be locked in a different order and result in the graph, in the path in the graph, which results in a deadlock. In order to solve this issue, we introduced data partitioning. So we carefully partitioned the data and process each partition, so that each partition can be processed parallel, and deadlocks are not possible. And then we process partitions one after the other sequentially. This allowed us to avoid the potential of deadlocks. Now, to dive deeper into the vector search, I'd like to hand things over to my colleague, Varuni.
Thank you, Konstantin. It looks like the slides disappeared. Okay, amazing. Thank you. Now that the data is in Neo4j, our next steps was to make it semantically searchable and then start with vector indexes. Our goal was to create vector indexes for different nodes in the graph. And basically, the core entities, geos, tags, and reviews that we shared before, each of these entities is different in structure and meaning. And embeddings help us capture those semantically similarities. The model can understand that NYC and New York City refer to the same location, and that live music and music venues are related tags. We use different embedding models to balance accuracy and performance. So lighter models for short text names like geos and tag names, heavier models for long form content like review sentences. And Neo4j gave us a lot of flexibility here. It allowed us to have multiple vector indexes per graph. So we can isolate different embedding types. We can also have multiple vector indexes per node, and even different embedding dimensions per index, which lets us fine-tune for quality and speed. That flexibility was crucial because it allowed us to mix representations within a single system. But we did hit one challenge, which is partial search. Neo4j currently doesn't support filtering a vector search to just part of the graph. For example, to run a search only within a single destination. And if we run a global vector query, it would search across the entire dataset, all reviews worldwide, which wasn't efficient or contextually relevant at all. So for example, if someone searches live music in New York, we don't want to retrieve live music in London. So as a workaround, we created separate vector indexes for each destination. That way, every vector search happens within a scoped context, fast, efficient, and geographically precise. Once we had vector indexes in place, the next step was for us to scale vector search. And scaling search meant optimizing the balance between recall, precision, and speed. We adopted approximate nearest neighbors, ANN, search using HNSW indexes in Neo4j to enable fast recall while maintaining acceptable precision. We also scoped ANN by destination index we had created, which not only improved compute efficiency, but also gave us predictable performance. So queries in large cities like London and smaller towns like Nice behave consistently. Another big piece was the embedding strategy. We used MPNet and GTE-based models, but for different regions. MPNet is great for short, structured text like tag names. It captures those concise conceptual meaning. And GTE works better for longer descriptive text like reviews. It captures those nuances and sentence context. And using both gave us a balance between semantic depth and memory efficiency. We then tuned similarity thresholds to control for precision and recall. This is how we prevented music from matching musical instruments or pool from matching pool table. And finally, to handle the operational scale, we tuned the batch size and parallel job control. So Neo4j could process billions of embeddings efficiently without overloading CPU or memory. In the end, a combination of these turned Neo4j into a powerful semantic retrieval engine at a global scale. This is where everything comes together. We combine structured graph lookups with semantic vector search inside Neo4j to balance precision and recall. So we start with the tag-based retriever. If a query matches an existing tag, say rooftop bar in Bangkok, Neo4j just follows the tag POI edges that already exist in the graph. That's fast and exact. But if no tags exist, say live acoustic music in New York, the semantic retriever kicks in, and the semantic retriever searches across review embeddings and finds conceptually similar phrases, such as band plays every Friday night, or great acoustic set upstairs. And these reviews connect back to the POIs, giving us new meaningful results even when no explicit tag exists. We then merge the results from both retrievers. And to refine the quality of the results, we applied two modeling layers. First, a cross-encoder re-ranker that rescores each query review pair, prevents mismatches like pool versus pool table, and an LLM-based judge in some nuanced cases to check final contextual accuracy. For example, refining a list of authentic Chinese hot pot restaurants. So altogether, by doing this multi-stage process, we get high recall, high precision results that truly matches traveler intent. So a query like romantic jazz restaurant in Paris returns not only tagged venues, but also places where reviews have mentioned live saxophone every evening. The final result is a system that doesn't just search, but it learns. Each retrieval cycle updates our graph and makes it more complete. When a query aligns with an existing tag, we detect untagged POIs that should be linked and flag them for connection. And when a query represents a totally new concept, we treat it as a potential new tag validated by traveler reviews. This creates a closed loop learning process, sort of like a tagging flywheel. Search informs tagging, tagging improves retrieval. And over time, the graph becomes self-enriching, faster, cheaper, and complete. We rerun this on a regular interval to capture new reviews and new trends that are mentioned in the reviews, correcting for outdated edges along the way. And in our latest run, this process actually restored thousands of missing tag POI connections, introduced over 100 new tag concepts that didn't really existed before, all verified by our hybrid pipeline. This work was a collaboration across our machine learning, product, and engineering team, and our partners at Neo4j, Dave and Sam, helping us scale. If you'd like to explore the full technical details from ingestion to vector search, I'd recommend reading our engineering blog post linked on these slides. Thank you so much for your time.
Yeah, thank you. Thank you, Tripadvisor team. This was really probably one of the more fun projects to work on in the last year. And I know we have a couple questions, but the work that we did in partner with Tripadvisor really drove some of the new features in Neo4j, especially in the 2025.10 release that just came out. We've introduced a new vector type where we can now basically specify the size of the vector, the type of the vector, storing in Neo4j, which should help with performance, which should help with storage. And it's just something that you will want to take a look at in the latest 2025.10.1 release. The new drivers are supporting it, and we'll continue to enhance those capabilities going forward. There was a question earlier in the chat around the pre-filtering, and this was, I would say, one of the biggest challenges for us at Neo4j was how do we support, this continuous high performance that Tripadvisor needed and balancing the locations and the queries. So in Q1, we should have the pre-filtering ability, so we can now filter those queries on, music venues in London and just search that piece. So pre-filtering and returning results. And then I think the last thing I want to say is, the work that we did, we really dove in to understand how our vector indexes work. And a lot of this work really helped us understand memory configurations, and some of the documentation in our online documentation about configuring memory, configuring performance was really this partnership between us and Tripadvisor. So I think we'll hand it off. There are some questions that in the chat, I think are best for the Tripadvisor. So I'm going to ask that you guys jump back on stage and let's see if we can answer those questions.
So I can see a few questions in chat were already answered in chat. Let's start from the top. Yeah, you can run Spark code right on top of the Snowflake with Spark Connect to improve just performance. Yes, that's what we're doing, I think. But there is no limit to the better performance. How does it know if the search results you are tagging during the self-enriching process are correct? There was an answer, I think, we're using the LLM judge and runner to evaluate the results and precision. Did you consider extracting evolving new text during the process? Yes, definitely. We were missing this. We were thinking of designing a mechanism to somehow automate extracting new tags, and this project allows us to do this. We can provide the concept, which is not a tag, and get the list of POIs that are relevant to this. That's the great outcome of this project. Okay. Oops. Do you use weights on tags and reviews to indicate new words more relevant? So we do. Still, when we are showing the list of results filtered by tag to users, it's either yes or no. It's the tag is either assigned or not assigned. So there is a threshold. After some point, if we are sure enough, we decide that the tag is assigned. But underneath the weight, this confidence level can be used to sort. If users are searching for something for live music, there are places where we are more confident that live music is relevant, then they can be sorted higher. Okay.
And I can add on top of that question. So we at the time of ingestion, we only consider high relevance reviews. So there are reviews that we filter beforehand, like before ingesting to the graph, to make sure that the reviews that we have ingested in the graph are high quality. So that incorporates the timing of the review, the message in the review, the details of the review. So many different items actually participate into that.
I hope I'm not missing any question. The next one is, how many entities did you get your graph reduced by when doing tag graph temporal location search for doing an N comparison on the reduced set? I guess for Uni, are you the best person to answer this?
Sure, I think I did talk about this, but it's a great question. Efficiency was the key for us too. When we run the nearest neighbor comparison, we don't operate over the full global graph. Instead, we scope the search space by creating a separate vector index per destination and per entity type. So tags, location, review sentences. That means when a query like live music in New York comes in, we only search for New York specific review index, not the entire corpus. That reduces the candidate set by several order of magnitude, I would say, from millions of review sentences down to a few 100,000 per region, which is what makes NN comparison feasible in the real time for a use case. So rather than reducing the graph itself, we dynamically narrow the neighborhood using graph traversal and geoscope, and that's what gives us the speed and relevance.
Thank you. The next question, are new tags created and used without human intervention quality control? We do have the tools for manual curation of tags. The customer support is using them a lot. So there is a way for customer support or for the owner to contact the customer support and say this tag, for example, say this tag should never be assigned to my location. And then no matter what the automated process decides, this won't happen. So yeah, we do have the way for manual intervention into this process. Curious to know if there is any cache in place for the same queries, or every new query goes through the same semantic search and graph pipeline. So first of all, not a cache, but we can decide if we make a decision that the tag should be assigned, that we update the graph, and the next time we don't need to run the vector search. We just have an edge with the graph. That's how we can save on recomputing the same things again and again. If there are no other questions, I guess we can wrap up. Thank you. Thank you all again. It was a pleasure being here.
Thank you.
Thank you, everyone.